So very nice to be with you today for this automotive industry webinar. I'm Cyprian from midas NFX team, and I will be the presenter today of this automotive industry webinar. So we'll talk about two main subjects. The first one is the CAE role in automotive industry, and the second part will be about NFX applications in automotive industry, in safety area, and also how to use CAE in order to increase the rigidity of the car body. So let's begin with some simple facts. When you're using CAE in automobile industry, there's a lot of work to do. The first one is the CAD modeling of the car body. Then you have to do the mathematical modeling, so it is actually the modeling special for the CAE. Then you have to find an analyst to analyze all that, to make the right condition and everything. And finally, you will get, if you're lucky, the right analysis and predictions. Don't ask me why I choose this picture, but maybe you know. Okay, so all that make the CAE design. So the purpose of this is to go from a 3D model to the production of a real car. And the CAE will help in three things. So it will improve the performance of the analysis, it will decrease the development time, and also decrease the cost and the weight of your system. Now, in automotive industry, a lot of tests are required in order to guarantee the safety of the vehicle, for example. So, as you know, there's a huge cost in real testing, like this crash test on the right. And simulation gives also good results, so it can limit a lot the number of real tests you have to do. And of course, it will decrease the cost. Now, it can also predict the durability of a car and its component, for example. So another possible simulation is the durability of the components, so fatigue analysis in order to determine where you will have some yielding inside the parts. So mainly CAE gives 5 main benefits for car industries. The first one is the product development time, which is reduced. You have less costs, less manufacturing cost as well, and it increases the product quality, and also you have better innovation chance. So actually one thing, one of the initial investments and that one that will have the most influence on the final product cost is the investment on analysis and CAE analyst. So early investment will be small, but as you can see in this picture, the impact of the quality on the quality of your product will be high, and thus the product will take an advantage and bring more money to your company later on. So the CAE process of a car is quite complex, so I decided first to talk about these 3 phases where CAE is needed. The first part is what we call primary step CAE. So it is kind of upfront CAE, which is made in order to plan when you're planning the project of the car, in order to have a first view of what will happen for this design. The second phase is during the design step. So in this phase, the CAE is used to interact with the designers and to have fast verification of local design of the parts and the components. And finally, you have the last step of the CAE, which is the quality improvement and the safety control, and also norm verifications. So this is the real design process of a car. So as you see, it's quite complex. You have CAE, you have CAD, you have styling as well, and you have real tests. So all that is together. So sometimes you have to do CAE first, sometimes you have to do CAD and CAE at the same time. And so it's not like we think. It's a very simple process. I mean, first you do the CAD, you make the model, then you do one-time CAE at the end to verify if it's okay, then it passes the test. No, it's much more complex than that. It actually requires what we call upfront CAE in order to see. So it will be more clear with this graph. So as you see, there's two curves which are typical curves for companies who are doing CAE-based product development. So the curve in green is the one, let's say the usual curve, when CAE is, let's say, used in downstream in order to put out the fires. So what I mean by that is you do the product, you do the physical testing, and you see there's a big problem in your design. So at this time you will require to use CAE in order to find a way to modify your design and make it better. So this is a typical product cycle, but you see, if you apply this upfront CAE to help avoiding the fires before they happened, the curve will be actually less steeper. What I mean is that this is the effort divided by the work. So actually, it will take less resources, so less cost, and the production of your product will be faster. Now you have the comparison of an analytically driven design approach and a traditional approach. So in the first approach you have FEA and process simulation, which is very important inside the process, and this is the traditional approach. So you have a very big step for detailing, and then this step about the engineering change orders, you see you have almost none of this step here, because using the upfront CAE you will avoid all that. And final validation and loans, all that takes a lot of time. So you save almost 30% of the time using CAE analysis. Now there's not only a CAE, there's also fluid analysis, so CFD, for verifying, for example, the aerodynamism of your car body, for the design and the styling, and also it can be used for the components inside, which requires liquid analysis. Now we'll go into the second part of my presentation, which is about the presentation of midas NFX application in automotive industries. So kind of tests we did using NFX, and in which parts of car analysis do you require simulation. So I will talk about first about safety area. So the first thing we'll talk about is low speed collision. So I will show you right after what it means, but first I would like to talk about a bit why we do this kind of analysis. So there are some let's say norms, international norms, which are like the RCAR bumper test, which encourages the vehicle manufacturers to produce effective bumper systems. And this norm is used for assurance companies. So they use this to test the cars with front low-speed collision and rear low-speed collision in order to see of the cost of the repair you will have to do if it really happens. So you have some model of cars, so the K5, and you can see, for example, difference between these two models. The K5 has repair costs of 1,004, so the unit is in million of wons, so it's a Korean unit, 1,000 wons, sorry. So you see it's 1.4 million wons actually, and 0.5 million, so it makes a total of around 2 million wons for the reparation if you have this front and rear low impact. For another model, which is actually newer than this one, the cost will be higher, because the design is not the same, and you see that the cost is almost the double of the first one. So assurance company have a special process. They use the RCAR low-speed crash test standards in order to announce the repair calculation results, and then they can calculate the premiums for the insurance. So what the car company have to do is to optimize the damage and the car reparation of the vehicle. So this is an example of this. So this is a front low-speed collision and the rear low-speed collision. So let's see using a small video to show you what really happened. So there's an angle of 10 degrees and the collision speed is low speed, so around 15 and 16 kilometer by hour. Now the rear collision is a bit different. It's a moving wall which is pushed around the rear bumper. So these two kinds of tests, so this is the FEA model that have been made. So you have several components in your system. You see you have the impact bumper, the can crash, the side member, and you have the cooling system. So why we modelize this cooling system? Because actually it's a very expensive part in the car, so if it is broken, it will lead the expense on the reparation. So the analysis is to see if this will not be damaged during the impact. And here you have the FEA model. So you have this bumper and the side members, and here the body of the car is modeled using rigid links and concentrated mass. So you don't need to model all the car to perform this analysis. You can replace the main part of the body using this kind of concentrated mass. So you have the bumper, the dimensions, and this is the difference between two different crush cans. So for one you have 1.8 millimeter of thickness, and the second one I have 2.0 millimeter of thickness. So you see there's a difference. For only 0.2 millimeter of thickness more, it will protect much more your during the impact. And this is the animation of this simulation. So you can see here the bumper which is crashing against this plate, and it gives you a graph of the displacement against the load for these two different crush cans. So you can see the maximum load is higher, of course, for this the crush can with a smaller thickness. And what is interesting and useful to have is the value of the energy which is actually absorbed in the collision by this crush can. So you see it's almost 6. So if the total crash energy is around 11.1 kilojoule, it makes that 55% of the energy is absorbed during the crash. Now let's take a look at the rear low-speed impact. So in this kind of way, the model is a bit more complex because you need to model more the rear of the vehicle. There's a few parts to integrate, and here the same way the concentrated mass have been used at the center of gravity and connected to the other parts of the body using rigid links. So this is the different part of the model. So you see that the different parts have been assigned different stress strain curves. So, and this is the value of the yielding stress. So the part in red is actually the part which takes the impact. So it is the one which has the highest yield stress. And let's look at what happened during the collision. So the moving part here is impacting the side of the vehicle, and you have the progressive collapse of the rear part. Now what we want to know is what are the plastic strain which have been caused on the car body due to this impact. So you can see here all the stress, the parts where you have this plastic strain are actually the rockers on these parts, the side members, and the trunk lid on this part. So all the parts which had biggest plastic strain will have to be reinforced in order to take more of the impact. Now let's talk about the seat belt anchorage. So it is another test which is required for the safety of the vehicle in order to test the strength of the seat belts. So it ensures the reliability performance of the seat belt, and during the collision it will endure a constant load test. So here you have the model which consists of 248,000 nodes and around the same number of elements, and the seats have been modeled like that. So the load is applied with specific direction which are written in the codes. Now this is the different stress strain characteristics of the different materials, and this is the result. So you have a small video which shows you what actually happened during the physical test, and here the reaction in the simulation. Now the parts which are taking the more damage are the A-pillar upper, the anchor of the seat belt, the seat rail mounting. So you see it's very good to perform this kind of analysis because you can detect all the small parts which will take the more damage actually, and all that can be reinforced. Now we'll do a series of side impact, different type of impact actually. So the first one is the side impact on the door of the car. So the way to do that is to take a rigid cylinder of 12 inches which is positioned in a direction perpendicular to the side door, and then we apply the displacement on it in order to see the reaction force of the door. So you have two types. You have the initial crush, so displacement at 6 inches, and the intermediate crush with 12 inches. So this is the different parts of the system. So you have 5 different parts with different characteristics of the materials for plasticity. And this is the result. So actually, in order to fit the regulation, the initial crush resistance should be superior to this value, and same for the intermediate crush and the peak crush resistance. So in this case it fitted all the 3, so it means that our door was correctly designed. Now another kind is the door trim linear impact analysis. So in this kind of analysis, what is actually done is when there's an impact outside the car, you see the passenger inside will be impacted against the door. So we model the door and the armrest here, and there's an impactor model. So the peak force will be actually registered when the impact happened, and then the value of this peak force will tell you if the system is secure enough or not. So same here, you have the different parameters which are taken. Here the same plastic curve have been used. And here you have the results for the front door and the rear door. So it's interesting to see that actually the peak force for the rear door is less than 2 times less than for the front door. So if you perform this analysis, you will notice that the passenger on the rear seat will be less injured if you have such collision. So it's important to perform this kind of simulation to know. And now there's a series of head impact. So this is also another kind of test which is performed for the safety of the vehicle. So first one is the impact on the instrument panel inside the car. So you have impact zone and different angle which are required by the regulation. So here is the model. You have the real model and the FEA model. The impact point is around here. This is the system, which is composed also of a few parts with different stiffness. And now you have the result. So you see the head is impacting the part in the middle, and you have acceleration. So in this case, what is required by the regulation is the acceleration. So if you have an impact which is less than 3 milliseconds, less than 8 times the gravity, then it will satisfy the law. Otherwise it will not satisfy the law. So in this case we found it was 70 G, so it was okay. And impact are not only on this instrument panel, but it can be also on other parts of the car. So in this case there's another factor which is required, which is the HIC, head injury reference value. So it should not exceed 1000. Here is the model, so different parts considered inside this part of the car, and the impact here. So same, you have a registration of the acceleration, and then you calculate this value, HIC, which give you if it satisfies the law or not. So in this case it was superior to 1000, so it doesn't satisfy the law. So as you saw, this part had to be redesigned to meet the regulation. Now you have the Pedestrian Protection Child impact analysis. So in this case it will be outside impact of the head on the front part of the car, and we'll use the same factor HIC to test that. So this is the model with 6 different parts and different plastic curves. And here you have again a video of the real test, which is actually performed to do that. You even have a slow motion to see what happened to the to this part. And same, we register the acceleration and then the HIC value. So in this type of analysis it was also too big. Okay, now we'll talk about another type of analysis, which is not about safety area, but about the rigidity and how to improve the stiffness of the car body using FEA simulation. So a car body, as you can see in this picture, is composed of a lot of parts, and so it's very complex type of analysis. So the first thing to see and try to determine is the resonant frequencies and the mode shapes of this body, to have a basic understanding of the dynamic stiffness. So here we determined all the natural frequencies of the analysis. So, and this is the mode shapes. So this frequency you will have the front upper. So this here you can see it in the animation. And for 39 Hz you will have the rear torsion mode. Now, the analysis of the rigidity is made also through static stiffness analysis to analyze the torsion and the bending stiffness. So all that will help to improve the comfort and the stability of your vehicle. So here you have the example for the torsion and here for the bending. Now, again, for the front side rail stiffness, you apply a load here and you measure what is the reaction. Same for the rear stiffness. Now, another way that we have to perform the analysis is to perform a quasi-static analysis. So it is kind of a nonlinear static analysis, but which consider the time. So it's not real dynamic analysis for the moment, it's only quasi-static, and it is used to evaluate the durability of the vehicle through the twist calculation. And all the stress contour can be predicted in order to see what are the weak parts of the body and the parts that have to be reinforced. So here you can see the results of this quasi-static analysis. So all the stresses contour will give you the areas where you need to reinforce. So in this case, for the rear structure, you have some red areas here. So it shows you really the parts where you need more reinforcement on the car body. Now the body roof. So this kind of simulation is to improve also the stiffness of the body roof. So because you don't know if a rock will fall on the roof or not, and this is a result. So you have a pushing of the roof in order to view what is the nonlinear characteristic of this deformation. And you see here the curve, you have the initial stiffness, which is conserved, but when you reach this point you have a soft oil caning, so it's kind of dangerous for the roof, so it will make big deformations. So last step to verify the rigidity is to use the explicit code. So in using several load conditions which are like dynamic, so in this type of analysis, as you see here, what will be put here on the green arrow is an impact load, so shock. So we'll do a very like a sudden shock in order to see the response of the body on that. So the displacement will give you something like that with a maximum displacement, and you will be able to see the plastic strain level and where also you need to reinforce your structure. And of course the fatigue analysis is very important for the body, and this is something which is also difficult to test with real testing. So you can, using FEA analysis, input a body load like that, so which is with many cycles, and finally see what will be the fatigue stress. Now let's talk about the doors of the car, because it's a part which is also quite sensible. When the door is open and you apply like a load here, so you can think you are trying to pull the door in this direction. So in this case you have a big, you have also some displacement here around the area of the connectors. And the door shell stiffness analysis, so very important analysis. If you get your car kicked recently, you will know that you will need this type of analysis. It's a kind of very sensible part of the car actually, so it really needs to this FEA analysis to reinforce all that. So you have the load displacement and the reaction of the door accordingly. And of course the sitting hood stiffness. So you can imagine someone is sitting on the front of your car. So you'll need to test also several positions to know which part will be more vulnerable. So in this case, a person which is sitting on the rear of the hood will increase the deflection almost 2 times. So the analysis can give you such results. So this is permanent deformation. And model analysis of the trunk lead. So we do this kind of analysis because the motor is running at a certain frequency. So it's around 700 and 800 RPM. So when the car is in stopped position and the motor is turning, it will increase the vibration inside the trunk lead. So by identifying the natural frequencies of this model, we are able to see where and what will be the response of that. So it can cause some damage, as you can see here. So it's not big damage, but it's the removing, for example, of painting on your car due to vibration. So after a long time, if you see some painting is going off this kind of part of your car, it's because your trunk lid have not been designed correctly. So you can come back to your car manufacturer and complain. So here, displacement distribution of the trunk lid, and same, we're analyzing lateral and torsional stiffness. Now also, if someone is on this part, so the leaning fender stiffness. Okay, and now we'll talk about some specific parts of the car. So one of the parts is the brake disc, in which model analysis and frequency response is applied. So first of all, this is the typical brake disc. So we need to do this kind of analysis to understand the dynamic of the brake disc and what happened during the braking of your car. So the way to do the analysis is to represent the brake disc like that, and then you apply 2 types of dynamic loads which depend on the frequency. So you have one which is in Z direction and one which is in Y direction. So if I consider the cylindrical coordinate system, and then this is the kind of result you obtain. So let me explain a bit how you can read this result. The response of the Z direction load is in green, and the response to the Y direction load is in violet. So actually, the parts when you have a peak like that means that you are in a mode shape of the brake disc. So when you have 2 mode shapes which are at the same time very close together, this will create a squeal noise inside your brake disc, and it's also very dangerous for the durability of the brake disc. So in order to avoid this, you need to make some small design changes in order for the peak to be separated a bit more. So here you have two portions where the peaks are very close together, and here you have all the mode shape which are identified. So, okay, the normal mode shape, so for the disc. And when you are in this frequency range, you are actually the two mode shape are very close one and the other one. So it will increase the breakage. Now let's talk about another type of analysis, which is thermal analysis, which is also performed on this brake disc. Thermal analysis is made to evaluate the deformation caused by the temperature on the brake disc. So because when you brake, the velocity will be very high and increase the temperature of all that. So to analyze this, what we did is actually we cut this model, we cut a small portion inside the model, and we specified some characteristic, like the specific heat and conductivity. So here you have a description of the boundary condition applied. And all that is considering the vehicle speed, which is decreasing, so during the braking. And here you have the thermal deformation according to this. So you have a small video also showing that. And here the final temperature and the deformation result. So final temperature can reach 420 degrees Celsius and cause a deformation of 0.7 millimeter to your brake disc. Now a bit more complex analysis is consider the brake disc and the fluid, the brake fluid system at the same time. So here, how will the heat make the transfer between the brake disc and the system here? We'll use FE analysis also to determine this. So you have some difference between the middle small cars, large luxury cars and sports cars with different boiling point and at a dry state or wet state. So all that has been considered in order to see a difference inside. So here are the boundary conditions you applied. So you have the disc, the housing, the piston here, and the brake fluid, which is actually here. So the temperature will be taken at this point. And here you have the result. So the temperature distribution going from the disc inside the brake fluid system. And here is the input disc temperature and the output of the temperature given by NFX. And finally, the last analysis that I will talk today is the stiffness of knuckle. And so you can see vehicle testing, it's a part which is here. So when the vehicle is submitted to very high vibration, this can also break. So it's not a very complex model, it's actually only one part. So even a designer can perform this kind of analysis if the loads are well defined. And first of all, here you have some static stiffness results for different load case. So this is also an advantage of NFX, is that you can apply different load cases together and check the fatigue analysis of all that. So after applying all that directly, you can perform fatigue analysis in order to see on which point the breakage will occur. Okay, so now it's over for this project application. And what I will tell you for at the end is that usually in car industry a lot of different solvers are used. So for crash worthiness, for example, explicit analysis for LS-Dyna, PAM crash is used. For NVH analysis, Nastran or Radius. And for durability, again, Nastran or Abacus are used. So the advantage of NFX is that you can do all this analysis in only one package. So using NFX, you don't need to buy separate codes for doing separate analysis. You can have one model, you can have one model and one solver. So it's really efficient against these type of analysis. So the less efficient is when you have a lot of different models in different softwares and using different solvers. So when the company is doing this kind of analysis, it's very difficult to get the results because everyone is specialist of another software, then you have to couple the result together, etc. So the best efficiency to have one model only and one solver. So it is possible in NFX because all the example I have shown to you are using the same car model. So we model only once the car body with all the components inside. And then by cutting a part of this model to apply a certain condition on the rear, for example, rear collision, or by modifying a bit or taking only one small part of this model to perform local analysis, all that requires only one model and one solver. And it really makes you gain a lot of time. The other advantage is that NFX has a design mode which is made for non-CAE specialists. So the designers who are making the parts of the car can use NFX very quickly to check their own design. So for small systems or small parts of the car, all that the checking and everything can be done quickly. And as the software is the same for the designer and the analyst, the model can be transferred to the analyst directly, so they can see what the designer made and give him some advice to change his simulation. Okay, it's all for today's webinar. So if you want to know more about NFX and the different type of analysis, tutorials and everything, you can always check our YouTube channel. So we'll have the webinar on it, we have some demos, some user case and much more, and also some interview of some of our partners and users. And finally, if you didn't try NFX, you can request for the 30 days trial on Midas website. So just go on midasnfx.com and request for the trial, and you will have 30 days full trial of NFX. Okay, it's all for today's webinar. And now if you have some questions about all that, please ask them and I will try to answer them now. And then, okay, so if you have questions, you have a chat section here in the panel. So you can just write it easily in the section and let me know. You can also let me know what you thought about this webinar, if you like. Okay, I see there's no question today. So I think, oh sorry. Oh, I have a question about composite materials. Okay, so yes, a composite material can be modeled as well in NFX. So layered composites, the layout can be defined, and NFX can directly give you the results of the composite matrix, for example. And it supports linear analysis and nonlinear analysis as well. So you can use composite for linear static, nonlinear, and also explicit analysis. If you're interested about composite, we had a composite webinar about 2 weeks ago, so I can send you the video about that. Okay, do you have some more questions? Are implicit and explicit solvers available in the same package, or are they different? Yes, they are available and they are in the same package. Yes. So you can use implicit, you can use explicit as well. So as you see, this example I've shown today, there's no implicit example because implicit was released only this year in NFX. But right now that we have this implicit analysis, it's really more convenient to perform more quickly nonlinear implicit analysis. So actually, you can even perform sequential nonlinear dynamic analysis, so you can couple the explicit and implicit together, and all that in one environment. Do you have more questions? How about the coupling with fluid, I mean CFD? This is a good question, and yes, NFX can also perform some kind of coupling. So what you can do in NFX is to perform CFD analysis in the same environment, and then you can extract the pressure on the model, so the pressure which is created by the fluid, and then you can create a structural analysis and apply this CFD pressure on it. So it's not what I would say, it's not yet a coupled fluid structure interaction. It's what we call an uncoupled fluid structure interaction, but it gives you a very efficient way to know the pressure on your static model, which are caused by the fluid, and it's quite convenient. We had also a CFD webinar which is available on YouTube, and I explained in this webinar how we can apply this kind of load and what is the kind of coupling we provide in CFD analysis in NFX. Okay, seems like I don't have more questions. Well, thank you very much for joining this webinar about midas NFX. I hope you enjoyed it, and if you need some materials, we'll send you the video and also the PDF of this webinar. And you can always ask me some question to my email. So my email is cyprian@midasit.com. So I wrote it into the chat section. So you can write the questions to me, and I will directly answer you. So don't hesitate to contact me if you have interest on one specific type of analysis, or you want to know more about the product. Okay, thank you very much, and see you next time. So we'll have a webinar next week, I think, about static analysis and a basic presentation of NFX. So if you have some time, you can join also next week webinars. The date will be available on Midas website. Okay,